Hello everyone, and welcome back. In this tutorial, we're going to take the Cyclone Separator geometry we created earlier and move into the next stage of the workflow, setting up an anisotropic flow simulation inside STAR-CCM+. This is a very interesting case because the flow inside a Cyclone Separator is dominated by strong swirl, three-dimensional boundary layer effects, and internal recirculation. That makes it a challenging CFD problem, even for a relatively simple geometry. In this tutorial, we're not trying to build the final high-fidelity model yet. Instead, the goal is to create a solid starting simulation with a coarse but meaningful mesh, the right turbulence model, proper boundary conditions, and a workflow that takes us from an initial steady solution into a more realistic unsteady solution with curvature correction. So let's get started. We begin by loading an existing simulation file that already contains the Cyclone geometry. If you already completed the 3D CAD Cyclone tutorial, you can use your own Cyclone.sim file. Otherwise, you can use the sim file provided by this training. Now that the geometry is available, the next step is to create the fluid region. Because this is a 3D CAD model, we first need to convert the CAD bodies into geometry parts, and then assign those parts to regions. So go to Geometry, then 3D CAD Models, right-click the Cyclone model, and create a new geometry part. Accept the default part creation options. That operation creates the geometry parts from the CAD model, and in this tutorial we end up with two parts, the main body and the outlet pipe. Next, assign those parts to regions. Expand the Parts node, select both the main body and the outlet pipe, then assign the parts to regions. In the dialog, choose Create a region for each part and create a boundary for each part surface. Apply the settings and close the dialog. Now two fluid regions are created, one for each part, along with the interfaces between the two regions. Let's open the geometry scene and add the regions into the existing surface displayer. Now, open the main body region and select the boundaries one by one. As you select them, they become highlighted and you can see their location and position. Then set the inlet boundary under the main body region to velocity inlet. Then go to the outlet boundary under the outlet pipe region and set its type to outlet. After that, expand the Interfaces node. Two sets of interfaces are created. The one that appears on the circular surfaces are internal interface, where we need the flow to be interpolated between regions. The over interface that appears on the cylindrical surface should be treated as baffle, so set its type to baffle interface. So now the region structure is ready. The inlet and outlet are defined, and the interfacial sides are treated correctly for this cyclone flow setup. Now we move on to the mesh. In this case, we use a combination of the surface remesher, polyhedral mesher, and advancing layer mesher. This is a nice combination for swirling internal flow because the polyhedral mesh handles recirculating flow structures well, while the prism or advancing layers help capture the near-wall behavior. So create a new automated mesh operation under Geometry, then Operations. Select both parts, main body and outlet pipe. Then choose the three meshers in this order: surface remesher, polyhedral mesher, and advancing layer mesher. Confirm the setup. Now edit the default controls of that automated mesh operation. Set the main values as follows: base size to 0.0125 meters. Target surface size to 80% of base. Minimum surface size to 30% of base. Surface curvature to 72 points per circle. Surface growth rate to 1.3. Number of prism layers to 5. Prism layer stretching to 1.2. Prism layer total thickness as absolute. with an absolute size of 0.012 meters and volume growth rate to 1.1. Now, let's define two refinement parts. The first one is a cylindrical refinement through the middle of the cyclone to better resolve the swirling core. Create a new cylinder shape part. Set the start coordinate to 0, 0, minus 0.3 meters. The end coordinate to 0, 0, 0.9 meters, and the cylinder radius to 0.03 meters. Add the created cylinder part to the geometry scene. Add it to a new surface displayer. Then go to the Scenes folder and adjust the opacity of the surface displayer. Make the first surface displayer also transparent. Now, you can clearly see how the cylinder is located inside the cyclone. Then create a second shape part, this time a block, to refine the mesh around the inlet region. Set the block corners to corner 1, minus 0.21, minus 0.11, minus 0.01 meters, corner 2, 0.023, minus 0.055, 0.11 meters. Drag the created block and drop it into the geometry scene. Add it to the surface displayer too. In the geometry scene properties, and for each surface displayer, change the color mode. Set it to distinguish input so the displayer colors different parts with different color. Now connect those shape parts to volumetric mesh controls. Under the automated mesh custom controls, create a new volumetric control for the cylinder and rename its cylinder refinement. Assign the cylinder part to it. Activate custom size for both the surface remesher and the polyhedral mesher. Then set the custom size to 50% of base. After that, create another volumetric control for the inlet and rename it Inlet Refinement. Assign the block part to it. Activate custom size for the surface remesher. Activate custom total thickness for the advancing layer mesher. And activate customize polyhedral mesher as well. Then set the custom size to 50% of base and set the prism layer total thickness to absolute, with an absolute value of 0.008 meters. With all of that in place, generate the volume mesh. Once the mesh is done, open a mesh scene so you can inspect the result. At this point, the cyclone geometry should now be fully meshed and ready for physics setup. Now let's define the physics models. For this tutorial, the simulation is set up as three-dimensional, gas, segregated flow, constant density, steady at the beginning, and turbulent. Under turbulence, the tutorial uses Reynolds averaged Navier-Stokes, K-omega turbulence, SST Minter K-omega, wall distance, and all Y plus wall treatment. Once the models are selected, save the simulation. Now we can move on to the flow boundary conditions. For this case, the inlet uses a uniform velocity profile together with turbulence intensity and turbulent length scale. Go to the inlet boundary and set the turbulence specification method to intensity plus length scale. Then set turbulence intensity to 0.0045, turbulent length scale to 0.000525 meters, and velocity magnitude to 10 meters per second. Create a scalar scene. Then create a plane section under derived parts. Use the main body and outlet pipe regions as input parts. Set the origin to 0, 0, 0, and the normal to 0, 1, 0. Display it in the existing scalar display and create the section. After that, change the view orientation so the view is normal to the plane. You can also change the projection mode to parallel. Then edit the scene settings. Deactivate the outline. Set the contour style to smooth blended. Set the scalar function to total pressure in the lab reference frame. And use the blue-red balanced color map. Now we are ready for the first run. Now click Run. The solver starts. The residual plot appears automatically. And once the case reaches the full default iterations, which is 1000, the scalar scene should show the total pressure distribution through the cyclone cross-section. When the simulation is finished, we can look at the residual plot. It seems the flow is not converged yet, so we need to increase the number of iterations. So, go to stopping criteria and activate maximum steps, setting it to 1500. That should give us a steady-state run that is long enough to produce a reasonable initial solution before moving to the unsteady part. At this point, we need to save the steady result so it can be compared later with the final unsteady solution. Under Solution Histories, create a new history file named Cyclone Flow Solution. Set the function to total pressure in the lab reference frame. Remove the default region entries so that the input becomes the plane section instead. Then create a snapshot and name it steady. This gives us a saved reference state from the steady run for later comparison. With this tutorial comes to its end. In the next video, the most important parts of the tutorial, switching to unsteady flow with curvature correction, will be presented.